Well, hi everybody, it's Brian Russell again, and today I'm going to talk about the rock physics template and the RockSI options in the Geoview log crossplot. As a way of introduction, the log crossplot in Geoview has had its own built-in set of rock physics templates for many years. Many of you may have used those. We call them RPTs. But what we were finding is that the number of templates were far fewer than those we found in RockSI. RockSI had a much richer set of templates and petroelastic models. Also, if we wanted to add a new template into the existing program, it required valuable programming resources. So what we decided several years ago was to stop adding new features in the built-in option and build a link to RockSI for template building. That's not to say we're not supporting the built-in function anymore. It's just we're not adding new features to it. So you can still use, if you've been using those features and like them, you can still use them. We're not going to take those away. But now you have an added RockSI option. So what I'm going to do in this talk is review both the existing RPT interface, in case you're not aware of it, and that's in Geoview, and also the links to RockSI. Now, one thing to note is that this, if you're using the RockSI link, it requires that you as the user owns a license to RockSI. So you're not going to get that unless you own a RockSI license. So for this talk, I'm going to use our classic colony logs, which you've probably used in either a course or going through a guide for AVO. Initially, they lack an S-wave. They only have the P-wave and the density. So what I've done here is I've created the S-wave log using the Mudrock and Gassman options, and then I've created the P impedance density times P-wave velocity and VPVS ratio logs and display them there on the figure. You can see P impedance on the left, VPVS in the middle, and I've shown a gamma ray. And then I've also displayed the V quartz and V shale logs and colored them in. Crossplot these, I go to the crossplot logs option and set the parameters as shown here. So we go to crossplotting, crossplot logs, and note there's a lot of other crossplots you can do, seismic, logs and seismic, horizons, data slices. But today I'm going to be focusing on the crossplot logs. And you can see I'm going to crossplot VPVS versus P impedance, where P impedance is going to be on the x-axis and VPVS ratio on the y-axis. All right, so under the parameters tab at the top of the page, I'm now going to set the depth range between 550 and 710 meters. That's where the best part of the logs are. That's where the zone of interest is. Also, the density log is not logged over the whole depth range, so this actually includes the full density values. So here's the initial crossplot with P impedance on the x-axis, as I mentioned, and VPVS ratio on the y-axis. And initially, the color will indicate depth. Now, what you can see is a number of clusters here, and this goes back to a classic paper by Odegaard and Avseth in 2003, which if you haven't read already, it was an extended abstract from the EAGE, you may want to download. And what they do is they identify these various clusters. Gas sands, cemented sands, wet sands, and shales. In fact, we have clustering and classification options to identify these built into the crossplot program, and I think I did an earlier presentation on that, so I'm not going to review that today, but it's something you may want to look into, find that archived discussion. The other thing is, do we really want depth as our color scheme? In this case, not. I don't want to use depth. So I've changed the color attribute. I've gone to change color attribute by actually right-clicking on the color bar and changed it to gamma ray. And now you can see more clearly the lithology indicated on this plot. So for example, you can see that the gas sand points, which are nicely separated down here with low VPVS and low P impedance, are colored yellow, which basically indicates their gamma ray. And if you went back and looked at the gamma ray log, you would see that those corresponded to the gas sands. All right, so All of the crossplot options are in the upper right part of the crossplot display, so you can look at the, you've got a create Geoview RPT template. You can also look at the name in this display. You can look at you can select different templates as you build them. Here's the icon that launches the Geoview RPT menu, Rock Physics Template menu. Here's the icon that will launch the Load RockSI PEM model option. And finally, here's the color palette option, which I'll talk about later. And I'm going to refer to Geoview templates as Rock Physics Templates, RPTs, and RockSI templates as petroelastic models. But of course, you can use those words interchangeably. All right, so let's start by looking at the RPT options in Geoview. What I first did was selected New from the RPT, or the Rock Physics Template menu. As you can see, that's the option at the top of the window. And I've created New. I've said New, and you can see it's created a default template called Crossplot 1 and drawn it on here. Now in this template, we're going from very low porosity on the right-hand side of the plot to high porosity on the left-hand side, and we're going from high gas saturation, low water saturation at the bottom of the plot to 100% water saturation at the top. And you can see the fit's not that great initially. So what I can do now is I can click on the icon that will bring up the default parameters for the template. And as you can see, the calculation is done using the Hertz-Midland. The default is the Hertz-Midland equation with the Hash-Strickman lower bound. If you pull those menus down, you can see that we have other bounds like the Hash-Strickman upper bound, the Voigt bound, the Royce and Hill bounds. And as you pull those up, you can see the plot change. Also, the fluid and matrix tabs up here are available, as well as different RPT types. We've got shale, quartz, limestone, and dolomite RPT types. So although I defaulted the fluid parameters, here's the detailed menu. You can see from that menu, there's an interactive ternary plot in the upper right-hand corner that can be used to specify the amount of each fluid. The water, oil, and gas tabs allow you to specify the properties of each fluid, the salinity, salt content, and so on. And percentage. Actually, you can put different salts, NaCl, KCl, and CaCl too, if you want. And we can also do bubble point calculations, patchy saturation. You specify the temperature and specify the pressure. And there's defaults for those. I also defaulted the matrix parameters, but here's the detailed menus, which include a mixture of N minerals. So for example, if you have a single mineral, you specify the moduli there. In this case, K modulus of 40. This is for the sandstone, 44 gigapascals for the bulk modulus, 44 gigapascals for the shear modulus, and 2.65 grams per cc for the density. But you can then go in and define a number of different minerals and a different mix. So here I'm doing 70% quartz, 20% calcite, 10% clay, and of course I can specify, as I look at each of these, I can specify their moduli and densities. I also went in and changed the effective pressure to 5 megapascals or 0.005 gigapascals, the coordination number to 9, and the upper porosity to 30%. And I got, and as you can see in here, the upper porosity is now, well, I start at 5% and I increment by 5% going up in it's 6 increments, so it gets you up to 30%. And I got a reasonable fit now, a little better fit than I got before, but it's, as you can see, it's still not perfect. So what I did then is I changed the K-dry option to user input, and I manually changed K-dry up to 2.35. Now, as I was changing it, as you scroll through those values, the curves move automatically, which is kind of a neat feature. And note, I've now got a very good fit for the gas sand and the cemented sands. Now, just because you're obviously forcing the fit here, so it doesn't necessarily mean you've got the optimal values from an actual physics point of view, but you have got a much better fit now. So that's basically the summary, a very quick summary of how to do the existing rock physics template. So what I'm going to do now is switch to the RockSI approach. So the first thing we want to do is load a petroelastic model, or a PEM, and you go to the load rock physics model icon at the top of the crossplot, which I pointed out is a kind of folder with a check mark in front inside it. So that icon will load the models, and so what I'm going to load is, so you'll see this interactive menu come up, and I'm going to select this option here that I've just put a little red box around, and that will allow me to load one of the models. Now I'm going to load the unconsolidated gas sandstone, which is similar to the model we have. Well, the math is identical, but the parameters or selection are slightly different. So this is similar to the one I just did in our rock physics template, which, by the way, is pretty much the only model in rock physics template. But if you want, you can bring any of the other models in, the carbonate models, the empirical models, and so on. And you can see there are multiple sandstone models too, all the way down to clay rich and so on. So we'll bring that unconsolidated gas sand model in, and initially the model will not be filled in. So I started with a set of reasonable parameters for the lithologic pressure, pore pressure, V shale. I've actually set V shale to 0. I can change that if I want. Temperature, salinity, gas water ratio, and gas gravity. And I also changed, I have a main gradation, which is porosity, or phi, going from 0.5 increments to 0.3 in increments of 0.05 or 5%, and water saturation is going from 0 to 1 in increments of 0.1 or 10%. I then adjusted, actually these are my final parameters, I adjusted them to get a better fit to the cross. As I said, we've got porosity and water saturation incremented. So note, we've also linked to the RockSI module, and as long as, of course, you own a license, so that the usual icons are at the top of the page. So for example, if you click on the question mark icon, you're going to get the documentation. And it's a very complete set of documentation with figures and references and so on. So it will tell you how this unconsolidated gas sandstone model was built. So you can also click on the pencil icon. That brings up the basic RockSI PEM script, and you can look and see what the parameters are. For example, you can see, let's take an example of we built the KM, the bulk modulus of the mineral, using a hill average and so on. Now you can also, if you want, you can go into the kind of gear icon at the top of the RockSI PEM script, and that will allow you to actually edit this. So for example, we could move options from the input variable to the output variable, or vice versa. We could change parameters. We could say, I don't know, effective pressure. Maybe we want to put in a BO coefficient in there if we want. That's a more advanced way of doing it. And then we would have to add a new parameter that has the BO coefficient and so on. But right now we're just going to use the default parameters. So here's the actual crossplot points. If you remember, if you think back to the plot we had earlier, it's very similar to the previous one. I'll superimpose it in a second so you can see the actual comparison. Although the theory for this model is exactly the same in both programs, there are more parameter options in RockSI, so we haven't quite adjusted the two curves to look exactly the same. So what I did was I actually went to the RPT selection, and I superimposed both crossplot 1 and the unconsolidated gas sandstone crossplot on the same plot, and you can see very, very close, but not quite identical. So of course, you could go back in and adjust your parameters to get an exact fit if you wanted. So as I say, although different choices were made, this fit is quite close, and you could go through and optimize it if you wanted. All right, so I talked earlier about the color palette. What I'm going to do now is apply this color palette to the PEM template. And I'm going to select the icon furthest on the right at the top of the screen. It looks like an artist's palette, so it's pretty easy to identify that icon. So the default color template is shown here, and I've applied an opacity of 50%, so you can actually see through the colors. And so when I do that, it actually puts the colors on where it's colored each grid cell, which is bounded by 5% porosity and 10% water saturation increments. What I'm going to do now is show, although we could go back and superimpose this on the wells, what I want to do is show a different, I'll switch to a different case study where I actually projected this color scale onto the seismic volume. Okay, and this is again a talk I gave earlier, a much more extensive talk, and I think it's recorded and you can find it in the archive if you look for it. And this example used a 3D inverted pre-stacked seismic data set and 3 wells over a field from the North Sea. Actually, there is a 4th well, well A, but it was outside the seismic volume. So this was an oil sand play and the location of the field's confidential. And the blue line, which you can see here, is an arbitrary line that I extracted from the 3D volume so that I tied the 3 wells together. So let's have a look at this inversion. So first of all, let's look at well B, showing P impedance, VPVS, and in this case, porosity and facies. And the green facies, the light green face, sorry, the dark green facies represent the oil sands. So here's the pre-stack inversion P impedance extracted from that line. So that line that I extracted, sorry, I should say the line I extracted from the 3D volume. And here is the pre-stack inversion VPVS. And you can see quite clearly low VPVS between well C and well D and well B and well D that correspond to the low VPVS ratio, also in the same position. Actually, more so between well C and well D. So what I'm going to do now is actually interactively pick 3 zones. I'm going to pick a zone, zone 1 in red, which has low VPVS and low P impedance. Zone 2 has high VPVS and low IP, low P impedance. And zone 3, the yellow, has medium VPVS and high IP. Actually, I think I did an earlier presentation that's online that showed how to do this interactively, and it's a lot more fun to do it interactively because you can move the zones around and actually see the cross-plots changing. But that be that as it may, I've actually in that location the cross-plot looks like this. So here's the VPVS versus P impedance cross-plot of the 3 picked zones. And these appear to correlate with the hydrocarbon sands in red, the shales, and the cemented sands, similar to that cross-plot I showed you earlier from the well logs, and similar to the interpretation that was given by Odegaard and Avseth. So what I can do now is I can superimpose the petroelastic model template of SW versus porosity on this cross-plot, so you can see porosity again increasing from right to left, and water saturation increasing from down to up, low to high on the plot. And I adjusted the V shale, and in this case I did adjust the V shale and the pressure. I don't share the parameters, but that's how I got the best fit. Put a bit of V shale in there, I think 20%. And note that the red points from the oil sand show higher porosity and lower water saturation as expected. And also for the other points seem to be explained by that template. So what I'm going to do now is fill in a color template for the for the RPT, and each color will fill in a grid cell as this delineated by porosity and water saturation increments, as I explained before, and we've used a rainbow type color scheme. So here's the plot. Here's the application of the new color palette with opacity turned on so we can see the points. Although the oil sand shows up as orange, the rainbow colors seem to make it quite busy. So what I'm going to do is I'm going to change the color palette. I'm going to initially set all the colors to white, and then I'm going to refill them with different colors that correspond to those points. So you can see I've colored the points that correspond to the oil sand as red, the points that correspond to the shales and wet sands as blue, and then the points that correspond to the cemented sands as yellow. And now when I go back and project, I can project those back onto the seismic section, and they show the shales in blue, the cemented sands in yellow, and the oil sands in red. And these actually give a pretty good fit, although to really do a detailed analysis, we should really use the LithoSI program from that's also part of the SI suite. That would give you a more confidence, and it would actually it's got more detail. But this is a nice quick look analysis that can be done using just the inversion results and the combination of, as I say, of the inversion results in Strata, the cross-plot program in Geoview, and in this case, I'm using the RockSI template. So it's a nice combination of different features that you have in our software. Okay, so that concludes a fairly quick overview of these options. So just to summarize, the log crossplot in Geoview has its own built-in set of rock physics templates, as well as an integrated link to RockSI. In this overview, I showed you how to use both options and illustrated the application using both a shallow gas sand from Alberta and a deeper oil field play from the North Sea. Note that you can apply both the Geoview and RockSI templates to crossplots derived from both well data and inverted seismic data, and then that the templates can be filled in with a user-edited color palette and then can be projected onto the seismic volume. So hopefully that's given you some things that you can take back to your own workplace and play with your own data and get similar results. Well, thank you very much, and I look forward to any feedback.